All right. So the threats to internal validity are called confounds. Basically, those are the ones that affect internal validity. Testing effect, repeated testing leads to better or worse out scores. Like I said, if you have a test and you've got like 500 questions on it and you're completely giving it to them all the time, then they're going to start doing worse on it because they're just going to be like, yeah, I'm filling in, I'm filling in. They're going to start making designs out of the fill in points and all kinds of stuff. So uh, eventually, the regression to the mean, so all the extreme scores are going to eventually tend to move toward the mean. So you won't have people on either end. The people who do really well will eventually, the mean will start to move up also. And so the ones who were doing poorly, after they get some practice at it, will also do better. So those are internal validity. And it's just right there on page 242. You've got all the internal validity issues, the confounds. And so, uh, well, it's not really a confound. It's some of it is experiment or it does influence it, test and retest. That was one of the issues because anytime that, especially if the tests are really similar, then they're really going to do it a lot better, right? So um, it's important to, if you're going to do test and retest, that you mix up the test enough that it works better, so that people aren't just going, "Oh yeah, I remember the answer to this." You know what I mean? Yes. And so those are one way to help with like the experimenter effects is to have a single blind experiment and double blind experiment. And so the single blind is when the experimental procedure is the subjects or the experimenters are blind to the manipulation being made. And then the double blind is when both participants and the experimenters are blind to the manipulation. So they don't know. And so it's takes away from the experimenter effects and it takes away some of the confounds caused by the subjects in practice. And so that's helpful. Threats to the internal validity is continued. We have the subject effect, the placebo group. Everybody's heard of the placebo effect. Just because you're taking medication, you tend to get better, even if it's a sugar pill, just because psychologically you start to feel better. So that's part of it. The floor effect and the ceiling effect is there's a limitation to how low people will go, and then there's a limitation to how high people can go. And the more people do something, they're going to more likely hit the ceiling effect. And the limitation for the floor effect is that the bottom will, it can only go so far. Eventually, they're not going to go any lower, and that's the floor effect. So external validity, that is the ability of the results to be generalized. So how if I have a really specific experiment in a lab setting, how well does that actually match the real world? Well, chances are it's probably not going to match the real world because we're looking at really specific conditions. And so that doesn't help. The college sophomore problem, when we have a bunch of experiments and they're done specifically with college sophomores, how well is that going to apply to people who have already graduated or professionals in the field? Or, at a time, there was mainly just Caucasian members of a college population. So it was white college sophomores instead of, a diversified color or base from which to choose from. And, for those of you who've maybe gone the traditional route of school, being a freshman is different than being a sophomore, which is different than being a junior. So there are those effects too. And so if you're even looking at specifically college life, you're only getting the college life of a sophomore rather than the college life of a senior, which is really two different things, right? And so it's always important to have some caution when we generalize. When we replicate a experiment, we can do it exact replication. So the study is pretty much done the same way using the manipulation and measuring the variables in the original study. We can change it a little bit, differing the methods, and that's more of a conceptual replication. And you're probably going to want to know these to be able to match them too. So exact replication, conceptual replication, and systematic replication. And so those are probably going to be on your test in some form. So those are threats to the internal and external validity. And so all of this just right out of your book. It's pretty simple, and that's all chapter 9. Chapter 10 is correlated group designs. And so I'm not sure why they put them all in the same file or the same PowerPoint, but we're going to jump to chapter 10 real quick and look at correlated groups designs. So the correlated groups designs is an experimental design in which the subjects in the experimental and control groups are related in some way. So there's two ways to have them related. One is a within subjects design. And so this means the same group is actually going to be the experimental group and be exposed to all of the groups. So both the experimental and control designs. And so they're going to be in each condition. The advantages of having a within subjects design is that it requires fewer subjects than between subjects design, because you have to have, for between subjects design, you have to have everybody in the control group, then you have everybody in the experimental group. Well, within subjects design, everybody is going to go through the control group and everybody's going to go through the experimental group. And so it requires less time to do this, and it's increase in statistical power because everything else for the person is the same. There are some things that we need to do, though, in order for it to use it. So the problem within subjects design is you have to look at order effects. And so one group, you're going to do the control group and then the experimental group, and the other group, another half, you're going to have it go the other way. You're going to split them up, and you're going to have the experimental group and then the control group, so that the individuals, you get a better picture of what ordering has to do with it. Counterbalancing is used, especially when there's more than one experimental group going on. So you might have up to 4 or more, and so counterbalancing is important. And in the book, it talks about the Latin square, which is right here, and that is a counterbalancing technique in order to control for order effects. So if you had 16 people in your experiment, you would have 4 people in each group, and so one group would be ABCD, one group would be BCDA, DABC, CDAB, and so you're going to look at all the different ordering effects for each of those groups. A might be the experimental, or A might be the control. And so this group right here is going to get the control first. This one gets the control last. This one gets the control second, and this one gets the control third. And these might be other experimental conditions that they're looking at. And so that's how they're going to counterbalance it. So each one of those members is going to go through each one of those groups. And as you go through another group and as you go through another group, you might start figuring out some of that internal validity stuff, right? You might start figuring out, hey, I think this is what they're trying to do with us. And so you can start having those effects. Plus, the person is just going to keep learning, right? So that's also called the carryover effect, which is on page 263 of your book. Now, that's within subjects. The next group is matched subjects. And so they're going to be given some kind of demographic or some other type of variable that's related to the outcome, and they're going to be matched according to those variables. And the more variables that they can match, the better the match, right? So they're going to do their best to have matched subjects groups, and so they're going to use that with, as long as these 5 people or these 2 people have the same characteristics, then they're going to put them together. They're going to match them. Now you can see that there might be people who don't match anybody, so that's one of the disadvantages of it. And when we look at that, we've got the advantages. The testing effects of demand characteristics are minimized. Groups are more equivalent than those in between subjects design, and almost as equivalent as those within subjects. So it's trying to get the best of both worlds. They're trying to get the people that would be in the between subjects along with the within subjects. So they're pretty close. By matching them on variables, they're more like 2 people within subjects. They only have to be exposed to the experimental or the non-experimental group. And so the same type of statistics can be used within subjects and matched subjects. And the weaknesses of the matched subjects design are that they are more subjects are needed, which I already talked about. If somebody drops out, then that means their partner also drops out. So it can be greatly affected by attrition. And in general, it might just be difficult to find enough people who match along the same variables. So those are some of the disadvantages of the matched subjects design. As you can see, in both of these cases, they are between subjects and within subjects or matched subjects. Each group has its advantages and disadvantages, and so it's just important to see what's easier. If you have a lot of groups that are already kind of similar, then you might want to use the matched subjects if you think that you can get enough people with enough characteristics that are similar. It always goes by your research question, though, so that helps too. Any questions on Chapter 9 and a little bit of Chapter 10? So as you can see, we didn't even talk about statistics. We're going to do that here in a second, but let me pull up. No questions? Like I said, I'm going to do my best to make these tests as much vocabulary and understanding concepts and not so much about the mathematics. It'd be different if we all had like SPSS and could do some of these things a lot easier. Good. All right. So, and we just went over all of this. So, looking at the parametric statistics. So this is some of the concepts that you're going to have to understand, not necessarily math, but it is concepts that you're going to have to understand. And they should be familiar because we already kind of went over these previously. So you have your null hypothesis, your HO. You have your alternate hypothesis, your HA. This is a two-tailed test. It's two-tailed because we're just wanting to see if they're equal or not equal. So think of two-tailed test as either being equal or not equal. So is population 1 related to population 2? That's our null hypothesis. We're saying that they are. The alternative hypothesis, we want to reject the null. The alternative hypothesis is population 1 is not equal to population 2. Now remember, there's not as much power in this because we're not predicting how they are related. If we can predict how they are related, then that's powerful, more powerful. Okay. Now, when we can give a one-tailed test, so we're predicting which direction that the that it's going in. Okay. So the alternative, or the null hypothesis, H0, is going to be one or the other. So this population is less than or equal to this population, or we're predicting this population is greater than or equal to this population. So depending on which one we use, less than or equal to, or greater than, we are going to have our alternative hypotheses as this population is just greater than this population, or we're saying our population is going to be less than the general population. In almost all of your research that you'll see in your textbooks and other places, your periodicals, your articles for your paper, alpha will be typically set at 5%. So for parametric tests, the data fit a bell-shaped normal distribution. Certain parameters are known. So we will know the means, okay? And we will know the standard deviation. We have to use interval and ratio data, okay? The two highest levels of information. So with the correlated groups t-test, so what group are we going to use this with? Correlated groups. A parametric inferential test used to compare the means of two related, so within or matched subject samples. So if I had to fill in the blank, I would say what parametric or blank t-test is going to be used within subjects or matched subject samples. What's the answer? Hello? So the question is, you have, so fill in the blank. Blank t-test is a parametric inferential test used to compare the means of two related within or matched subjects samples. That would be something that's probably going to be on your test. So you have to be able to know that it's, anybody? What's the answer? Correlated groups. Yep. Correlated groups t-test. It's right there on the screen. I'm not doing anything tricky here. So, all right. So when t-tests are given, you're going to get your t, right? These are the degrees of freedom. This is the result, the test result, and then it's going to say whether or not the p was less than 0.05, or sorry, 0.5. And this is a one-tailed. All right. When a result is significant, the p-value is reported at less than 0.05. Okay, so this one was wrong, actually. They have it written wrong here. It could be 0.05. The p-value or alpha level indicates the probability of type 1 error. We want this probability to be small, right? So now here are the assumptions for the correlated groups t-test. Same as for the independent groups t-test, except the observations are correlated. So to go back to the independent groups t-test, we are looking at in chapter 9. We didn't go over it because it wasn't on the slides. But if you go back to your books, chapter 9, If you go to page 244, the very bottom, are y'all there? Okay. So for parametric tests, such as the t-test, inferential statistic designed for sets of data that meet certain criteria. The most basic requirement is that the data fit a bell-shaped distribution, so a normal shaped distribution. In addition, parametric tests involve data for which certain parameters are known. So we know the mean and the standard deviation. And finally, parametric tests are use interval ratio data. So the same exact things, right? So just keep those things in mind. So on page 249, another phrase that you're going to have to know is effect size. And the effect size is the proportion of variance in the dependent variable that is accounted for by the manipulation of the independent variable. Cohen's d is something that measures that. Okay. And so what it is saying is that there is a portion of the dependent variable that is accounted for by the manipulation of the independent variable. The bigger that portion is, so if this is my portion, the bigger that portion is, the greater it is. So we want it to be as much as possible as big as that. But if it's only that small, then it's a very small effect size. And most of it's unaccounted for. So the bigger that portion is, just look at it from your hands. If it's that small, then it's not very good. If it's bigger, the effect size is bigger, then that means more of the dependent variable accounts for the manipulation. Okay? So if you go to page 251, right there in black and white are the assumptions for the independent group's t-test. Okay? The data are interval ratio scale. The underlying distributions are normal. The observations are independent. If we could compute the true variance of the population represented by each sample, the variance in each population would be the same, which is called homogeneity of variance. If any of these assumptions are violated, it is appropriate to use another statistic. Okay. So on page 251 are the same assumptions. For correlated groups, we have the same assumptions, except that the observations are correlated. Okay. So now everybody knows where to find the assumptions, page 251. Any questions on chapter 10? Oh, oh, okay. Thanks for, see, y'all should have spoke up earlier when I had them on the screen. No, I'm sure it's probably when I closed it down that I think it closed it. Okay, well, that's what I'm saying is that nobody told me that you didn't see them. No. So next time I put slides up, let me know that you can see them or not see them. All right. And you all have them anyway, so if you were going along. I'm getting ready to put chapter 11 up. Chapter 11, there we go. Right now, y'all shouldn't see them yet. I haven't got that far yet. All right, do y'all see it now? Okay, so chapter 11, not bankruptcy. So now we're going to get to the next level of complexity, which is more than two levels of an independent variable. So far we have been dealing with one control group, one experimental group, one group in A, one group in B. Now we're going to have multiple levels of an independent variable, okay? So basically what this is talking about is ANOVA. And now with ANOVA, we are looking at, if we go to type 1 error on page 283, about halfway down, it talks about how with more groups, there's more type 1 error. And so we have to account for that. And one of the ways to account for it is by making adjustments. And so, and I just want you all to understand, the only concept that I want you to get out of this is that there's more error. And because there's more error, we have to adjust for that error. Okay? And so when you see that, you're going to see things like Bonferroni adjustment. And what you're going to know about that is that it's one way to correct for the error that is happening because of multiple levels. Okay? You're likely, if you're in your book, the reason why we have more than two levels of an independent variable, for several reasons. It allows researchers to compare multiple treatments. It enables them to compare multiple treatments with no treatment. And more complex design allow researchers to compare a placebo group with a control and experimental groups. So that's why we have these higher levels. The Bonferroni adjustment, which is what I was talking about, and it sets a more stringent alpha level for multiple tests to minimize type 1 errors. Just because every time you add another level, you're going to add more error. And so this is one way to adjust for that. Probably remember that sentence right there. It's probably going to be something similar to it on your test. So other advantages in comparing more than two kinds of treatment in one experiment, it reduces both the number of experiments conducted and the number of participants needed. If you can have groups in more than one, then you're saving time and money. And usually that's what it comes down to. So as you can see, we have the, in A, we have the full experiment. So we have the control, the moderate, and the high. And then we look at, with anxiety down here and the exercise group over here. Now we're going to break this apart. So now we're going to look at the control group and the high group here. And as you can see, it's a straight line that goes across. That's one way to compare the data. The next way is the control group and the moderate group. So then you have the control group and the moderate group. And as you can see, it's a pretty steep going down. And then you have the moderate group and the high group. So we're comparing this one and this one, this one and this one, this one and this one, and then we look at all of it. So from one experiment, we have 3 different relationships when we have 2 levels of the experimentation going on. Okay, or sorry, 3 levels. We've got control, moderate, and high. So you're going to get used to seeing these, and you're going to have to see be able to talk about those. When you see this group here, you're going to know that it's actually 3 separate groups that you're looking at, because you're going to compare the one group twice and each group twice. All right. So adding a placebo group improves an experiment by a more accurate assessment of the therapy's effectiveness. So it accounts for spontaneous remission and controls for participant expectation effects. Remember, if the participant knows that they're taking medication to get better, the chances are pretty good they're going to start to get better. So again, when we look at the using more than one level, we can look at the type of statistics we're going to use. We can use multiple t-tests, because for each one of these, we can do a t-test, right? Because there's just 2. Or we can use ANOVA, which will look at all of them together. And so ANOVA can do that. Using multiple t-tests increases the chance of type 1 error. So then when we adjust for that by using ANOVA, and we use it with the Bonferroni adjustment, that increases the chance of type 2 error, right? So remember, type 1 error is the false alarm, okay? So we don't want false alarms. You know, if you go in for a drug test, you don't want a false alarm. You don't want them thinking that you're using drugs. So when it's type 2 error, then that is we missed the alarm, okay? So we don't want to miss these. These ones aren't good, but they're better than type 1 errors. When we look at using 2 levels, it allows for comparisons of all the treatments within the control. And so remember, you're going to look at each individual one as well as the overall effect. And ultimately, it allows for the placebo group. So now, I mean, we can still do ANOVAs in things like, we could still do it in like Excel. If it's set up right, you can set it up and do it in Excel. I actually, when I did my master's program, I actually took ANOVA, a whole class on just ANOVA, and I could do it all by hand with a calculator. And so it is possible to do these things by hand, but it's not fun. It takes a long time. And so we don't have to worry about that. Like I said, I'm going to do my best to not have math involved in this. We'll see where we go along. For the chi-square, we might go back and use some math, but for this stuff, it's just, like I said, I had an entire semester in my master's program just on ANOVA. So it's important to know how to do it if you're going to go on. Most of you are not going to go on for your PhD, I don't think. If you are, then you should really be paying attention. One-way randomized ANOVAs, an inferential statistic for comparing the means of 3 or more groups using a between subjects design and one independent variable. Okay, so here are the conditions for using a one-way randomized ANOVA. It has to be a between subjects design and a one independent variable. So if I had a question on the test and it said I'm going to use, for my experiment, I'm using a one-way randomized ANOVA, and there's some things to select from. Maybe it's a multiple choice with multiple selections, and there's 4 things there. One of them is a between subjects design and an independent variable. That's what you need to pick, right? This is the stuff I want you to know for the test. Why would you use a one-way randomized ANOVA? Because you have a between subjects design and you have one independent variable. Okay? Affirmations? Is anybody there? All right. So I just want to, I want to make sure that y'all are understanding what I'm saying here. So, all right. So when we look at, we've got a group here. We've got a rote, rehearsal, imaginary, imagery, and story. We have 8 subjects or 8 participants in each design, and each one, as you can see, has their own mean. X bar 4 here, X bar equals 5.5, X bar equals 8. And then there's a grand mean. So a mean of the means is 5.83. Same thing. You just add 2, 4, 3, 5, 2, 7, 7, or 6, and 3. You average it out, you get a 4. You average these out, you get 5.5, and you average these out, and you get 8. The grand mean is the average of all of these. And so, and you could add 4, 8, and 5.5, and then average it by 3, or divide it by 3, and you'll get 5.833 as well. But I like to do it though with all of the numbers to get the grand mean, because rounding can affect whether or not you get an accurate grand mean. So, analyzing the multiple group experiment. The grand mean is the mean performance across all participants in a study. So the error variance is the amount of variability among the scores caused by chance or uncontrolled variables. So that's the error variance. You may want to know that definition. Within groups variance, the variance within each condition, an estimate of the population error variance. So the between groups variance is an estimate of the effect of the independent variable and the error variance. The F ratio, which is what you get your F statistic, the ratio between groups variance to within groups variance. So between groups variance to within groups variance. So here's the within groups, and here's the between groups. Okay, so to go back to here, within this, there is a variance. Okay, so that is the within groups variance. Within this group, there's variance. Within this group, there's variance. And within this group, there's variance. Okay, now there's between groups variance too. So between this group and this group, there's variance. Between this group and this group, there are variance. And then between this group and this group, there are variances. So it's important to know all of those variances. That's how we're going to ultimately get our F statistic. So between groups variance divided by within groups variance equals a systematic variance plus the error variance divided by the error variance. Okay. Again, probably not going to have to deal with too much math. If there's anything that's math-wise that's going to be on the test, I will post a separate video going specifically over any math that will be on the test. Okay? That would be great. All right. For an F ratio to be significant, it must be substantially greater than 1. If an F ratio is approximately 1, then the between groups variance equals the within groups variance. So there's no effect of the independent variable. The total sum of squares, the sum of the squared deviations of each score from the grand mean. Okay, so total sum of the squares from the grand mean. And that's going to give us this. So the grand mean, remember, is 5.833. So 2 minus 5.833 squared is 14.69. 4 minus 5.8 squared, and then square it, is 3.38. 3, there you go, 5, right? Because it's only 0.83, square that, you got just over 64.64. So that's what you do here. You're going to sum up all these squares, and that's the sum for group 1. That's the sum for group 2, and that is the sum for group 3. The total is 127.32. All right. So that is the sum of squares total. Within group sum of squares, the sum of the squared deviations of each score from its group mean. The between group sum of square, the sum of squared deviations of each group's mean from the grand mean, multiplied by the number of subjects in each group. So the mean square, an estimate of either variance between groups or variance within groups. So between groups, you're going to get that. And the degrees of freedom is k minus 1. Within groups is n minus k, the number minus k, and the total is n minus 1. So you're going to get all of these. You're going to get between groups, you're going to get within groups every time you do research using ANOVA. Now, I know I'm just going over this. I don't expect you to know all this stuff, okay? I just want you to know where it comes from. So over here, you get your mean square. For between groups is SSB over degrees of freedom B. Within groups is SSW, degrees of freedom W. So within groups, between groups. Your F statistic is your mean squared between and your mean squared W. So this number divided by this number, okay? So that's how you get your F statistic. And all it's doing is looking at the difference in the variation, okay? And then we have eta squared, which is an inferential statistic for measuring the effect size with ANOVA. And so eta squared, n squared looks like. Eta squared is the statistic between and the the sum. Went too far. So sum squares total for the between divided by the sum squares total for everything. So here are the assumptions for ANOVA. And these are the things that I want you to know, right? I want you to know the assumptions. So the assumptions for the one-way randomized ANOVA, data are on the interval ratio scale. The underlying distribution is normally distributed. The variances among the populations being compared are homogeneous. And observations are all independent of one another. So violations of some of the assumptions do not necessarily affect the results. So post hoc tests. When used within ANOVA, a means of comparing all possible pairs of groups to determine which ones differ significantly from each other. So Tukey's, honestly significant difference. So Tukey's HSD, a post hoc test used with ANOVA for making all pairwise comparisons when conditions have equal ends. So the requirement is that there be the same amount of groups or same amount of people in each group. And in this case, we could do Tukey's HSD because we had the same. We had 8 people in each group. So one post hoc test that we could do is Tukey's. And so this would be the formulation for Tukey's. And again, we're not going to do the math, so don't worry about it. One-way repeated measures, ANOVA. And so before we had one-way one-way randomized, right? ANOVA. So one-way randomized. And now we're going to talk about one-way repeated measures. And this inverse statistic test is for comparing the means of 3 or more groups using a correlated groups design. So not a between groups, but a correlated groups design and one independent variable. Okay. So we now have our data here. And these are now within subjects study. So looking there, that's the key word there, within subjects. Study of the effects of rehearsal type. So within subjects means that the same group went through rote rehearsal, they did imagery, and they did story. And so as you can see, the grand mean, it's a little bit tighter. The other grand mean was 5.8. This one, we're looking at 5.03. The rote rehearsal was a little bit lower. This one was a little bit lower, and this one's a little bit, actually it might be higher, huh? Nope, lower. Ooh. And it kicked you off again. Sorry about that. Let me get you back on. Sorry, got a little crazy with my wheel here. So that first part was between groups. Okay, so one-way repeated measures is for correlated groups, so within groups, and one independent variable. And so remember, all these people are the same people. So all the people in this group, all the people in this group, and all the people in this group, these are their scores. So now we're looking at the subject and the between, and then the error, and then the total. So we added our added one extra here. Now we're looking at the subject, the sum of squares subject divided by the degrees of freedom subject, sum of squares between degrees of freedom between, and sum of squares error degrees of freedom error. And our F statistic now is on the mean sum between and the mean sum error. Okay. And so that's what we're going to use. We're going to use this one and this one before we used for between subjects this one and this one, which is why this is more powerful statistically, because if you remember from chapter 9 and 10, we talked about this being more powerful. So assumptions of the one-way repeated measures, the data are interval, normally distributed, the variances among populations are homogeneous, and the groups are correlated. So that's the thing that's added, right? The groups are correlated. And now non-parametric statistics for multiple group experiments. Kruskal-Wallis test is appropriate when the data are ordinal So in order, right? Or if the involved populations are not normally distributed. So if it's not a nice curve, if they're not normally distributed. So this is an analogous test for use within subjects design. The Friedman rank test is for that. So here are some things when we use different non-parametric statistics for multiple group experiments. Non-parametric. So remember that. So the Kruskal-Wallis test, when data are ordinal or not distributed normally. And then the Friedman rank test is within subjects design. So advantages of multiple is compare more than two kinds of treatment. They use fewer participants, compare all treatments with a control group, and you can use placebos. For randomized one-way ANOVA, we use it for the randomized one-way for between subjects. The repeated measures one-way ANOVA is used for correlated group designs. So when there's within subjects or matched subjects, okay? So that's why you use the two. So if I had a test question that said, why would I use one-way ANOVA, randomized one-way ANOVA versus repeated measures ANOVA, one-way ANOVA? And the answer would be between subjects designs for randomized and correlated groups for repeated measures. Any questions on chapter 11? Like I said, and if we were in class, I mean, in real class, I would probably have you do some statistics on the math, using math, but we're probably not going to do that. I don't know. So, so for the grand mean, you would just do the mean of all the participants. Yep. You don't want to just you don't want to just go by the means that they are have for each experiment or each level of experiment. So remember, the rote, rehearsal, the imagery, and the story are just the different levels of the experiment. And we could see, because they use the same experiment, both as a between subjects and as a within subjects design. So the experiment can be used either way. It's just what you want to do with it. And if you wanted to, you could also do it um, a matched as a matched correlation also, or a matched group study. So because that is also with a within qualifies as within. But like I said, we don't have statistical um, data. Um, it does show us how to do it fairly easy though in chapter 11 on page 314, how to do it in Excel. But I don't think I'm gonna have y'all do that. So, and then of course SPSS would be one of the best ways to do it. It's pretty easy. Okay. All right. Thank you. Any questions on chapter 11? All right. Chapter 12. Just pulling it up here. Can everybody see it? Okay. So chapter 12, complex experimental designs. So as we continue to build, now we're looking at using different levels of design, using designs with more than one independent variable. So more than one variable that we're manipulating. And the coinciding statistical analysis of complex. So using designs with more than one independent variable. So we have a factorial design, a design with more than one independent variable. The advantage is it allows us to assess how variables interact. And complete factorial design is one in which all levels of each independent variable are paired with all levels of every other independent variable. From it, we will get main effects and interaction effects. So the main effect, an effect of a single independent variable, and the interaction effect, the effect of each independent variable across the levels of other independent variables. So how one independent variable affects the other. So you're going to get the main effect, the single independent variable. So if we have three independent variables, we'll have three main effects, one for each one for each variable, independent variable. And then we're going to have interaction effects. So how did the first independent variable affect the other two, and then all the way until we look at all the different relationships. So again, using our numbers, we're looking at rote, rehearsal, imagery, rehearsal, and column means. And so, and the independent variable is the word type, variable A. So we have rote, rehearsal, imagery, rehearsal. Our column means are 7.5, the abstract is 5, and the main effect of B, and is 5 is 7.5. So looking at it from rote, which goes this way, and imagery. So looking at the main effect, no interaction effect between the abstract and the concrete. We have, so the two levels of our variable are abstract and concrete. And there's no interaction effect, no main effect between those as far as word type, number of words recalled. The main effect of A and no main effect of B, no interaction effect. So A condition and B condition. Sorry, that thing's popping up. So possible outcomes of a 2x2 factorial design with rehearsal type and word type as independent variables. We look at these. So abstract and concrete, we have one, and then we have no effect. And then we have an interaction, right? So when we see things crossing over, that is an interaction. So on a test, I might give you a variety of graphs and say, select which one is interacting. This one is not interacting. They meet, but there's no interaction. There's interaction here. So sorry, no main effect of A, no main effect of B, and no interaction effect. No interaction effect, sorry, and then interaction effect. So if they touch any place, they're interacting. Interaction effect, interaction effect. No interaction effect, no interaction effect. And if this one came all the way up here to this point, it still would be no interaction effect. They have to actually touch to have an interaction effect. So when you see those graphs on the test, maybe know that there's an interaction effect anytime that they touch. So basically what I want you to get out of there is the types. There's no main effect because it's flat. If there's any type of change in elevation, either up or down, there is some type of effect. Main effect A, main effect B, main effect, main effect. No interaction effect. So main effect of A, no interaction, or main effect of B, an interaction effect. So basically just being able to look at a graph and say whether there's a main effect or an interaction. So a two-way ANOVA is similar to a one-way ANOVA. The difference between groups of variance may be attributable to factor A or factor B and the interactions of factor A and factor B. So the word type, independent variable A, so we have two levels, right? Concrete and abstract. And then the column means of the main effect of A, the grand mean of 6.25. So looking at our concrete and our abstract, the cell mean is 4 and the cell mean is 5 here. So we have rote rehearsal, imagery rehearsal. So two independent variables, right? Rote rehearsal, imagery rehearsal. Two independent variables, so a 2 by 2. And that's how you know what the number is. Somebody have a question? It is, but it's getting a little bit more complex. But yes, the means. So if you see now we've got different cells. So if we looked at it as if this were a square and this were the dividing line, this cell here has a cell mean of 4. So these ones here, the mean is 4. These ones here, the mean is 4.5. This one here, the cell mean is 5. Sorry, cell mean is 6. And this one here, the cell mean is 10. So cell mean of 4 for here, cell mean of 5 for here, cell mean of 6 for here, and the cell mean of 10 for here. So the main effect of A is 7, the column means. And so looking at this, the main effects of B, sorry, I'm going to sneeze. Maybe not. Okay. If you look at the main effect of B is the cell mean and the cell mean 4.5. So 4 plus 5 is 9. 9 divided by 2 is 4.5. The row means are these. And the cell means are these. So the column means, the main effect of A is the cell mean plus the cell mean divided by 2. So 4 plus 10 is 7. 4 plus 10 is 14 divided by 2 is 7. The cell mean, or the main effect of the abstract is, oops, sorry. 5 plus 6 is 11 divided by 2 is 5.5. So that's how you're getting your main effects from this chart here. The grand mean is 6.25, which is what we're going to use with the ANOVA. Okay. So writing these out, looking at the analysis, we've got X minus X bar. So we've got rote concrete, rote abstract. Then we've got imagery concrete, imagery abstract. So all we're doing is taking each of these, rote and concrete, rote and abstract, imagery, concrete, imagery and abstract, and then we're putting these in here. So we're getting this, the sum of squares for rote concrete, sum of squares for rote abstract, sum of squares for imagery concrete, and the sum of squares for the imagery abstract. Okay, and we're adding these all of these up to get the sum of squares total, which is 202. The math for these really isn't that bad. It just looks weird because you have all these different symbols. Okay, so now the sum of squares factor A, the sum of squares deviation scores of each group mean for factor A minus the grand mean times the number of scores in each factor A condition. Okay, so now we've got these x, the sum of A, sum of G minus the sum of G squared times the eta A. So we're going to go through, and that is sum of squares A equals 18. Sum of squares B equals 98. And then to do the sum of squares of the interaction, sum of squares A times B. And so what we're going to get when we do this is 50. Like I said, I'm not too worried about you figuring out what the how to calculate these. I want you to know what they are as far as definition. So the sum of squares error is the sum of the squared deviations of each score from its group mean. The within group sum of squares is a factorial design. So now if you notice, there's 3 F statistics that we're going to get out of here. So we're going to get one for factor A, one for factor B. We're going to get the interaction between A and B, and then there's the error, and then there's the total. So we get these, we're going to figure it out. We would get the sum of this, the sum of B. That gives us sum of squares A divided by the degrees of freedom A. And then the MSA is the MS error. So when we figure out this number here, we divide this number by this number. Same thing for factor B. And each of these will have an F statistic. So factor A, the word type, the degrees of freedom was 1. The sum of squares was 18. The MS was 18. And the F statistic was 13.95. Factor B, the rehearsal type, Remember, these were the individual independent variables. Is 75.97. The interaction of A and B was 38.67 or 0.76. So when we look at it on a table, the number of words recalled as a function of word type and rehearsal type, we get this. Okay. And by rote is this one, and then by imagery is this one. So this one's steeper, and it seems to be like there is some more power there. This one was in the negative. So with abstract words being more difficult, do these touch? No, so there's not an interaction here per se. So for statistical analysis of complex designs, here are the assumptions of the two-way randomized ANOVA. Used when you have a factorial design. All conditions contain independent samples of subjects. The interval or ratio data are collected, and their populations are represented by the data, are roughly normally distributed, and all have homogeneous variances. Two-way repeated measures ANOVA, similar to two-way randomized ANOVA, more advanced statistics are required. Okay, so mixed ANOVAs, one variable is manipulated between subjects and one within subjects. So you could actually do it between subjects and within subjects. Three-way ANOVAs, there's going to be three main effects, three two-way interactions, and one three-way interaction to interpret. With MANOVAs, there's an advanced statistic. Again, these ones are more complex than ANOVAs, and interpret them in a similar fashion to statistics we have already covered. So using meta-analysis, advanced statistical procedures, combines, tests, and describes the results from many different studies. Enables us to draw more objective conclusions about the generalizability of research findings. So if you had a bunch of ANOVAs that were done over a variety of different experiments that were all geared towards the same thing, you could use meta-analysis, which is an advanced procedure. So combining all that information into one big research study looking at generalizability. That was a whole lot of information there. The biggest thing is, are you able to see where the main effect is? And is there interaction? Okay. Page 326 of your book in chapter 12, it looks at the possible outcomes of a 2x2 factorial design with rehearsal type and word type as independent variables. So when you look at it, you can see A, no main effects, no interaction. Looking at B, there is a main effect of A and no main effect of B, no interaction effect. So looking at C, there is a main effect, or sorry, no main effect of A, there is a main effect of B, and no interaction effects. If you look at D on page 326, you can see that, so basically know where page 326 is to look at whatever kind of graphs I put up. There's a main effect of A, a main effect of B, no interaction effects because they don't cross. For E, there's a main effect of A, a main effect of B, and an interaction of effect. Looking at main effective A, no main effective B, and an interaction effect. Looking at G, no main effective A, main effective B, and an interaction effect. And then H, there are no main effects, there is an interaction effect. Okay, so you might want to remember page 326, write that down so that you can see those quick graphs of the 2x2. Correct. So all of the ones on the right-hand side of that page are all interaction effect. Yep. All right, so that is chapter 12. And the assumptions of a two-way randomized ANOVA are on page 336. Any questions? Okay. That's all right. That's all right. So let's see. Let's go to chapter 13 then. We're almost through our chapters here. We already did chapter 15, so we've only got 2 more chapters to go. All right. All right. Chapter 13, quasi-experimental and single case designs. So conducting quasi-experimental research, types of quasi-experimental designs, the internal validity and confounds in quasi-experimental designs, and statistical analysis of quasi-experimental designs. So continued developmental designs, conducting single case research, and types of single case designs. So looking at this, basically a quasi-experimental design differs from an experimental design in the fact that there's not a control group or a comparison group. The independent variable is not a true manipulated independent variable, and participants are not randomly assigned. The bigger one is randomly assigned. Without randomly assigned participants, then it's automatically it's quasi-experimental. So non-manipulated independent variable, the independent variable in a design in which subjects are not randomly assigned to conditions. Instead, they come to the study as members of each condition. So for instance, um, looking at all the second graders in an elementary school. They're automatically just second graders. They're not randomly assigned, but we've got three different classes, right? So one class gets a control, one class gets some type of reading intervention, and a third class gets another type of reading intervention. And so we're looking at the effectiveness of those um, interventions. Nobody was randomly assigned to their class. They were already there. They were already set. So um, we are going to have to look at the kids are exactly where they're at. So it's a non-manipulated environment. Examples of quasi-experimental designs: John Snow's hypothesis: people contracted cholera by drinking contaminated water. And so um, correlational methods: two measured variables. The variables may be related in some way. We cannot conclude that the relationship is causal. A quasi-experimental method: typically one non-manipulated independent variable and one measured dependent variable. Systemic differences have been observed between the two groups or more groups, but we cannot say that the non-manipulated independent variable definitely caused the differences. Due to confounds inherent in the use of non-manipulated independent variables, there may be alternative explanations for the results. So, uh, using correlational methods, we can see that the groups may be related in some way. Using the quasi-experimental, may have been observed between two or more groups, but we cannot say how it was caused or if it was caused by the design. So there are different types of quasi-experimental design: single group post-test only design, single group pre-test post-test design, a design in which a single group of participants is given a treatment and then tested, a design in which a single group of subjects takes a pre-test, receives some treatment, and then takes a post-test. So many of this should sound pretty familiar. Non-equivalent control group, pre-test, post-test design, a design in which at least two non-equivalent groups are given a pre-test, then a treatment, and then a post-test measure. Multiple group time series design, a design in which a series of measures are taken on two or more groups both before and after a treatment. So, excuse me. Bless me. So looking at multiple group time series design, comparing Connecticut fatality rates with the fatality rates of 4 other states, used as a control group. So you can see um, the Connecticut in general stayed lower except for 55. Internal validity and confounds and quasi-experiment. Now, if you notice, we really didn't get into, we just looked at a number, right? These were the fatalities rates, and then compared to the 4 other states. Um, there's no cause, it's just actually just data that's being there. So the internal validity and confounds in quasi-experimental designs. Quasi-experimental designs never conclude that the independent variable definitely caused any of the observed changes in the dependent variable. Quasi-experimental designs lack internal validity. We don't know, it could be any of those reasons why we got the data that we did. So data collected from a quasi-experimental design analyzed in the same way as data collected through experimental designs. Conclusions must be tempered because of the confounds inherent in quasi-experimental designs. Basically, what it's saying is that we may get data, we may have assumptions that are made from that data, but we can't really show or prove it because we can't prove anything anyways, but that it's true. So the thing that we can get from quasi-experimental data is ways to set up um, some experimental, so it can lead into some experimental. Developmental designs, cross-sectional design, the type of developmental design in which subjects of different ages are studied at the same time. So that's cross-sectional. So you might be looking at first, third, and fifth graders, and then you're going to follow them through. A cohort is a group of individuals born at about the same time. So some lifelong Emmy Werner did some research on resilience, and she started with children born in Hawaii in the 40s, I think, and that research is still going on. They're still alive, so they're doing a cohort research, a lifelong cohort research of those individuals. Cohort effects, a generational effect that occurs when the era in which individuals are born affects how they respond in the study. So, for instance, if I were going to do a research on fear of flying, and if I have participants that are from before 9/11 and are old enough to know what happened during 9/11 and then post 9/11, so children who were born in 2010, 2011, there could be significant differences between those two groups based off of their experience with 9/11. That would be a cohort effect, a generational effect. A longitudinal design is a type of developmental design in which the same subjects are studied repeatedly over time as they age. And then a sequential design is a developmental design that is a combination of the cross-sectional and longitudinal sections. So you might have three different groups at different ages, but then also start doing a longitudinal study, like maybe a 10-year study of those first, third, and fifth graders to see how they ended up in their careers or whatever. So things like that. Single case studies, a design in which only one participant is used. A small N design, a design in which only a few subjects are studied. So types of single case designs, a reversal design. It's a single case design in which the independent variable is introduced and removed one or more times. And then the ABA reversal design is a single case design in which baseline measures are taken, the independent variable is introduced and behavior is measured, the independent variable is then removed and baseline measures are then taken. So you can see from ABA, before, introduced, after. Again, ABAB reversal design in which the baseline independent variable conditions are reversed twice. So AB. And so number of bites and pinches during the school day. And so this is for one kid looking at how it worked. Baseline, pointed finger, no for bites and pinches. No. There was a drastic decrease. They quit doing it. And so it rose again, not to the point where it was before, but then he continues after it and it drops down immediately back to almost the same level. And it's going to rise a little bit. So interesting. That's a one case design. So multiple baseline design, a single case or small N design in which the effect of introducing an independent variable is assessed over multiple subjects, behaviors, or situations. Multiple baseline design across subjects, small N design in which measures are taken at baseline and after the introduction. So again, all of this is probably going to be some kind of matching or recognition in some sort. So Dave, here I am. My baseline, pretty poor grades. After school tutoring, contingent on a D or an F. So raised all my grades. Roy, and they let it go on a little bit further for Roy. And now, because he's got used to those habits, maybe it's not as high as it could have been. And Debbie, we let go even further. And started to interact, and then by day 25, she'd only made so much progress. So that is a multiple small n design. Single case designs, multiple baseline design across situations. So looking at behaviors here, across situations here. And they're pretty self-explanatory. So looking at reading and math, slips taken for cries, whines, and complaints. And so the baseline was fairly in the middle there. And then after the slips are taken away, it declines greatly, returns back to the base, goes up a little bit, and then taken away, it declines completely. So looking in math, it declines, it actually stays the same, and then declines further. So some interesting ways to look at the single case or small n designs. All right, so no math in that one, which is nice. So we'll be looking at mainly just recognition. Um, just being able to recognize things. Um, you know, if I describe something, be able to match it to whatever design it was, whether it's a small n, an n, um, whether it's behaviors or situations. So basically, just knowing definitions and being able to look them up. Yeah, no numbers. So and basically with the quasi experimental design, you can do all the statistics that you can do in a regular experimental design. However, there's so many confounds and other things that you can't control for that the data really don't mean a whole lot, unfortunately. And then chapter 14, we're well ahead of schedule. That's pretty good. So now back to math in a different way. We're looking at chi-square and different things in this chapter. So let me pull it up for y'all. And we're almost done. Everybody see it? Okay. So chapter 14, non-parametric inferential statistics. So we have the Wilcoxon rank sum test, a non-parametric inferential test for comparing sample medians. So what's it comparing? Sample medians of two independent groups of scores. Sample medians of two independent scores. The highest rank should be equal to n1 plus n2, the first sum of the ranks, for the group expected to have the smaller total. Okay, so here are the assumptions. The data are ratio, interval, or ordinal in scale, all of which must be converted to ranked, so ordinal. So even with ratio, it has to be converted to ranked. The underlying distribution is not normal, so it's not a normal curve, not a normal display. The observations are independent. Wilcoxon matched pairs signed ranks t-test, similar to the correlated groups t-test, except that it's non-parametric and compares medians rather than means. So the correlated groups t-test is similar to this one, only it's looking at non-parametric, we're looking at medians and not means, okay? So almost all the non-parametric tests that we're going to look at here, all of them actually don't need interval or ratio data. They are looking at other ways to get information. So know the assumptions of the Wilcoxon matched pairs signed ranks t-test. It's hard to say that. The data are ratio, interval, or ordinal in scale. So all of which must be converted to ranked. So even though it's ratio data, we don't care that it's ratio. We want to look at the order that data is in because we're getting the medians. Remember, median is exactly the middle of the numbers of the data that we have. The underlying distribution is not normal, so it's not going to be a normal curve. And the observations are dependent or related. So those are the assumptions. So know those assumptions for the Wilcoxon matched pairs signed ranks t-test. The chi-square test of independence. This is a non-parametric inferential test used when frequency data have been collected to determine. So frequency data, so tally marks. How many people fit into this subject? How well an observed breakdown of people over various categories fits some expected breakdown. The phi coefficient, an inferential test used to determine the effect size for a chi-square test. And for a 2x2 contingency table, we use the phi coefficient where sigma is the square root of x squared over n. The assumptions of the chi-square test of independence. The sample is random, the observations are independent, and the data are nominal. So now the data, this is a test for nominal data, so just names. So you might be looking at males, females, Republican, and Democratic, okay? And so you'll get a 2x2 square or some other similar square, and that's what you use a chi-square for. So that was extremely quick. Let's look at your book. I'm surprised there's no more information on there. So looking at chapter 14. So for the Kruskal-Wallis test, just read that first paragraph and it tells you exactly why you use it. So instead of, we can't use an ANOVA, which would be appropriate, except for when the data are ordinal. So if we have ranked data, we should use the Kruskal-Wallis test instead of an ANOVA. Or when the assumptions of population normality or homogeneity of variance have been violated. And so the data used to collect the Kruskal-Wallis test are always ordinal or ranked. And so that's why you would use that. And again, it shows us all the numbers and stuff that we have to do. The Friedman test is also here. The Friedman test is a one-way repeated measures ANOVA. And so basically, we would use these in lieu of the other ones if some of the violations are done. And so If I ask you a test on anything on there, it'll be very simple. You probably just have to identify why it would be used. And the only, so a better table, page 379, is a table that you would likely see when using a chi-square. And yes, that's what you would see normally for a chi-square test. And so if you turn the page, it tells you how to determine it. And so when we look at the expected frequency, we have the row total over times the column total, and that is all divided by n. So 10,800 divided by 190 is 56.8. This expected frequency appears in parentheses in the table, and you see that 57. So if you notice, if you added up all the expected frequencies, you would get 108, and you would get 82. You would going across, you would get 100, and you would get 90. And so with 56.8 being the number, and we're dealing with regular numbers here, so we have to round them. 56.8 is 57, basically. 57 in that first box gives us 43.51 to get the regular numbers down. Okay. So when we look at 57 as being the normal for the upper left cell, right? So we put 57 there, and if that's the expected result for that one, then 57 plus 51 equals 108. 57 plus 43 equals 100. And then because we have 43 and 39 together equals 82. And so after we get the upper left-hand corner expected frequency, that's when we get the rest of the numbers. You have to do a little bit of math. Now, to get the chi-square, we have to get the total of the observed minus the expected squared divided by the expected. And so you just plug in numbers from there. 65 minus 57 squared divided by 57 is 1.123. 35 minus 43 squared divided by 43 is 1.488. 43 minus 51 squared is divided by 51 is 1.255. And 47 minus 39 squared divided by 39 equals 1.641. And that gives us a total of chi-squared equals 5.505. So then, looking at that, the degrees of freedom for this test are equal to row minus 1, column minus 1, where row times each other. So 1 times 1 is 1. the number of rows is, and C is the number of columns. So 2 minus 1 times 2 minus 1 is 1. Then we have to go back to Appendix A to identify the chi-squared for degrees of freedom 1 at the level of 0.105. And that's just going to give us the cutoff point in Appendix A. And that's only if we're going to have you actually do this. I'm not going to have you do this, even though this one's pretty easy to do. Okay, so basically all they did was, and this is, they are calculating the expected value for the top left corner. So 65, that corner, the babysitters and yes, they calculated that using on the next page, the expected frequency for each cell. So the right are the row total plus the column total. So the row total plus the column total, or times the column total. So the row total, row was it's 100, and the column total was 108 for that very top right frequency or top left frequency, right? So 100 and 108. You see those numbers? And I'm getting to the parentheses. So if you turn the page, on page 380, it tells you how you got that number. So you multiply for that square, for that one section, 100 times 108 divided by the total of 190. And that will give you your expected frequency for that one box, which is 57, because we round up, right? 56.5 and higher, we would round up, so 57. And now that we know the row total, or the expected frequency for that, we know that the column total is 108. 108 minus 57 equals 51. 100 minus 43, or sorry, 57 is 43. So that's how they get the ones in the parentheses. Do you understand that?
Okay, yeah, I follow.
And then now that we have 57, 51, and 43, the only number that we don't have is the 39 yet. And we can get that number either by taking 82 minus 43, which gives us 39, or we can take 90 minus 51, which gives us 39. And that's how you get those numbers in parentheses. Those are the expected distribution. If everything was equal, those were the numbers that would be expected we'd get. And so now we're trying to look at how it doesn't fit what our expectations are. And that's the chi-statistic.
Okay,
And then, so if you wanted to actually figure out the chi-statistic, you'd have to do the sum of each individual box. So the babysitter's yes is one box, the babysitter's no is another box, having taken the first aid course. The babysitters or non-babysitters yes have taken the first aid course, and the non-babysitters no have not taken the first aid course. And then you get the box. And from there, you do the math, and then you get your 5.507 on page 380. And then you go back to the back of the book for table A7, which is your information for your chi statistic, chi squared. So that's on page 441. With degrees of freedom at 0.05, you need to be higher than a 3.81, and 5.507 is, so statistically different, significant. And so, and then if you wanted to go ahead and check the the effect size of that, that would be the phi or the phi coefficient, and it's just putting your statistics 5.507 divided by the n and square root of that, and you get 0.17. So any other questions? All right, well, that's chapter 14. All right. So I'll probably have the test posted maybe tonight, but if not tonight, tomorrow. In 2 weeks. Yeah. All right. Well, thanks for coming. And yep, you're welcome. Hope you all have a good rest of your day. Okay. Bye bye.